If you pay attention to the ball and the tip of the rod in this clip, you'll find that the tip of the rod is falling faster than the ball. The ball is accelerated by gravity, and thus the tip of the rod is falling faster than the acceleration due to gravity. But why?
So here we have our free body diagram showing the three forces acting on our body. We have the force at the center of mass, which we say is a point-like particle in all of our equations. Then we have the normal force in the y direction, the normal force in the x direction, and we have our coordinate system labeled here. We also have the distance r, that is the length of the rod or lever, and then we have our distance L, which is the length from the pivot point to the center of mass. And then here we have our sum of forces equations in the x and y direction. We notice that in the x direction there is 0. It's equal to 0. The sum of forces is equal to 0, and so our normal force in the x direction is also equal to 0. We have our sum of forces in the y direction set to mass times acceleration, and that is n minus mg. Then we have our sum of torques equation equal to I alpha, and we have our torque of the center of mass, which we define down here by our force times the lever arm, which is equal to L times mg. And here we have our moment of inertia equation, which is m times L squared.
Alright, so then on the other side, we use the values that we found for the moment of inertia and for the torque around the center of mass, and we plugged it into this equation, the sum of torques equation. And solving for alpha, we found that alpha is equal to g over L. And so then we used a different equation. We used the equation the velocity in y is equal to the angular frequency times the radius. We took the derivative of that and we found that the acceleration is equal to the angular acceleration times the radius. And so plugging into equation 2, we found that plugging in this part for equation 2, we found that n minus mg is equal to m times g over L, which is the angular acceleration times the radius. And solving that, we found that the normal force is equal to 2mg. That's for part 1, finding the normal force. And for part 2, proving that it falls faster than the speed of gravity, we took this distance r and we took this distance r and replaced it in this final equation here. And the way we found the final equation is by saying that the acceleration is equal to g over L times r. That r in the first case is equal to L. So the r over L is just 1, and that's how we got 2mg. But in the second one, the r is equal to 2L because the center of mass is in the center. And so it's double the length. And so solving for that, we found that the acceleration is equal to g times L. And so the downward acceleration at a distance r, for r is greater than L, is larger than the acceleration at the center of mass, where r is equal to L.